Hello class, today we're going to cover section 1.7, one-to-one functions and inverse functions. We're going to cover 4 parts to this. First, we're going to determine whether a function is a one-to-one. Then we'll determine the inverse of a function defined by a map or a set. Third, we'll obtain the graph of the inverse function from the graph of the function, and then finally find the inverse of a function defined by an equation. Okay, so first, a function is one-to-one if any 2 different inputs in the domain correspond to 2 different outputs in the range. Now I'm going to use an example that I used earlier with this set, and I'm going to have a collection of inputs. So 1, 2, 3, and 4, those are the x's. And then the outputs, and the outputs will be our y's, so that would be 4, 5, 6, and 7. And this is one-to-one because each input maps to one output. So this is a one-to-one function. And again, it's because each individual input maps to one individual output. That's significant. Okay. Another way to determine a one-to-one function is the horizontal line test. Now, the one key thing here is it says that for every horizontal line intersects the graph of a function. That's critical that we understand it's a function f, and at most one point, then f is one-to-one. The significance of that is typically when we want to say something is one-to-one, graphically, we have it pass the vertical line test and then the horizontal line test. But since this is stating that this is already a function, it's already passed the vertical line test. So it's got to pass the horizontal line test then to be one-to-one. So I'll do a quick graph of a function. You all should be familiar with this function now. This is f of x is equal to x cubed. And to show that this is a one-to-one function, we need to take a series of horizontal lines. And really it's one line that's being slid up and down, but you can see that each horizontal line is only hitting the function at one point. Because it's only hitting it at one point, the function f of x is equal to x cubed is a one-to-one function. Okay, so it's a function because it crosses the vertical. It passes the vertical line test. It's a one-to-one function because it passes the horizontal line test also. Okay. We run into a theorem, and the theorem here tells us that a function that is increasing on an interval I is a one-to-one function on that interval. And by that same reasoning, a function that is decreasing on an interval I is a one-to-one function on that interval I. Basically, if you have a function, it's passing the vertical line test, and it's strictly increasing, it's going to pass the horizontal line test. And the same reasoning goes for the decreasing. So I'll just show you a quick picture. So if I had a function and it went like this, clearly from this interval, it's going to clearly be increasing, and it would pass the horizontal line test. By that same reasoning, if I had something like this, that's going to also pass the horizontal line test, and so this theorem holds. Okay. The next topic we're going to talk about is to determine the inverse of a function defined by a map or sets. And so our example here is to find the inverse of the following one-to-one function. So we're given a collection of points to create a one-to-one function. Now from here, what we can see, in order to find the inverse of this, all we're going to do is switch our x with our y. So our first point would then be negative 27, negative 3. Then the next would be negative 8, negative 2. Then negative 1, negative 1. And lastly 0 and 0. This would be the collection of the inverse. So this would be the inverse function. And again, like I said, all we're doing is switching x and y to do that. Now, to determine if two functions are inverses of each other, we need to verify that by doing two tests, this test and this test. The first one says that the inverse of the function will end up being x. The other says the function of the inverse function being evaluated is x. This is also considered a composite function. So composite functions, you may have seen them as like f of g of x. This is just another way of writing that. That's the same as going f of g of x. So basically the g of x in this case would be the inverse, and then if that equaled x, we would in fact have one side of the inverse proof. So let's do this example to show that. So the first example is going to be f inverse, or g inverse because we're using g, of g of x. Well, that's going to be g inverse is now going to be of x cubed because g of x is x cubed, and then we're going to plug in the cube root of x cubed because what ends up happening is this gets substituted in for that x, and so we get that. So the cube root of a cube of x cubed is simply going to be x. This is showing one direction. We have to show the other direction. So the other direction would be g of g inverse of x, and that's equal to g of cube root of x, which would then be the cube root of x raised to the third, and that again would be x, and that's showing it the other way. Since it shows it both ways, we know then, therefore, g inverse of x is the inverse of g of x. So when you're doing these problems, you're going to have to show it both ways. Inverse plugging into the original function, and then the original function being plugged into the inverse, and the results must be that they both end up equaling x. If they don't equal x, then they're not inverses of each other. Okay. The third thing we need to talk about is obtaining the graph of an inverse function from the graph of a function. And there's a theorem that goes with that says the graph of a one-to-one function f and the graph of its inverse function f inverse are symmetric with respect to the y equals x line. So the y equals x line is this line right here. So think of it as a mirror. So if I gave you a function that had the points 2, 0, 4, 2, and 8, 4, and it went like this. So again, this is 2, 0, 4, 2, and 8, 4. The inverse function then would be 0, 2, 2, 4, and 4, 8. And it would look like this. So again, all we did was switch x and y. And that is the inverse function graphically. See how that y equals x line works like a mirror for this inverse function. Okay. Now, to find the inverse of a function defined by an equation, f of x is equal to 2x plus 3. We're going to rewrite that as y is equal to 2x plus 3. And then what we're going to do is we're going to switch the x and the y. And once we've done that, what we need to do then is solve for y. So once we've switched x and y, solve for y. So then we're going to get x minus 3 is equal to 2y, and then 1/2 x minus 3 over 2 is equal to y. And then changing it back to function notation, it would be f inverse of x is equal to 1/2 x minus 3 over 2. That is the inverse, and you could test that by doing this method here to it. You should get x with both of those. Then here is a summary for you guys to look at for this section. I hope you found this beneficial. As always, all the best.